Okay, so the speed of an inline skater is usually described in meters per second. The speed of a car is usually described in kilometers per hour. How are instantaneous speed and average speed different? Well, average speed is computed over the entire time or duration of a trip, where instantaneous speed is what is the speed that you're traveling at that instant in time, at that particular instant. And it could vary. The example I always use is I get in my car, I'm driving to work. Well, the road in town here is only 25 miles per hour. So I drive 25 miles per hour till I get to a major road, and then the speed changes to 45 miles per hour. So if I take the total time it takes me to leave my house and get to work, and if I take the total distance and then divide it by the time, that gives me the average speed. But the instantaneous speed is the speed that I see on my speedometer when I'm driving. So speed is a ratio of the distance of an object as it moves within a certain amount of time. In science and in physics, the SI unit is meters per second. So a lot of times in my physics classes, we have to convert everything to meters per second. In some cases, you don't have to. It really depends on the question. But most of the formulas that we use in physics, we want to leave it at meters per second. Two ways to express the speed of an object are the average speed, and that's the total distance divided by the total time it takes to travel that distance, and then the instantaneous speed. How fast am I going right now? And so here's the equation for the average speed, so you guys could see it a little better. It's the total distance divided by the total time. And so in your reading guide today, I give you one problem where you're going to be given a couple different distances and some different times, and you're going to add them all up and divide the distance by the time. Now, the short formula for that is the average velocity, and we'll talk about the difference between speed and velocity in a second. So let's look at this. It says, while traveling on vacation, you measure the times and distance traveled. You travel 35 kilometers in about 0.4 hours, and then you travel 53 kilometers in 0.6 hours. What's your average speed? Now, this is almost identical to your reading guide problem. Basically, what you do is you add up the total distances, right? 35 plus 53, that gives you 88, divided by 1, right? So I think the average speed is like 88 kilometers per hour. That's pretty fast. Is that right? Yeah, that's pretty fast. All right. So let's crank through this. So we're going to take the total distance, 35 kilometers plus 53 kilometers. That means the total distance that I traveled was 88 kilometers. And the time that it took me to do that was actually 1 hour. So it'd be 88 kilometers per 1 hour. So a lot of times, and we'll do this a lot, as we enter into the physics portion of the ICP, physics is hard, but it's not hard. It's really just a lot of math. So what you want to do is you always want to list all the things that you know, list all the things that you don't know, and then figure out which formula contains the quantities that you're looking for. And then it's a matter of picking out the equation that works and then plugging in what you know to solve for the unknown variables. It really is that simple. It took me a long time to figure that out, but it's that simple. So in this particular case, we're looking for an average speed. We know the formula is going to be the total distance divided by the time. And so we just plug that stuff in, and that's how we get the answer. That's it. The extra work that we had to do was add up the distances and add up the times. So when you're done, I like to do this thing that we call a common sense check. Now, a common sense check is it's pretty simple. Like 88 kilometers, yeah, it's kind of fast. But if you look at a speedometer, that's about highway speed. So if I got 880 kilometers per hour, that's like, that's way too fast. So I always like to do a common sense check. When you're all done cranking through everything, does the number seem reasonable? And so this one does. This is like a typical highway speed. So let's do one more. It says a person jogs 4 kilometers in 32 minutes, then 2 kilometers in 22 minutes, and finally 1 kilometer in 16 minutes. What's the jogger's average speed in kilometers per minute? Now, this is the key thing. I think you guys have figured out we're going to add up all the times, add up all the distances, divide the total distance by the time. The difference is that they tell us specifically the units, and we'll talk about dimensional analysis a lot. We started off the beginning of the year talking about dimensional analysis, but we're really going to dive deep into that in the physics portions of this class. So our final answer has to be in kilometers per minute. So again, we need to know the average speed or the average velocity. So we're going to add up all the distances, 4 plus 2 plus 1, and then all the times. And so we've got 7 kilometers in 70 minutes, or 0.10 kilometers per minute. Let's do one more. 190 kilometers in 3 hours, and then 120 kilometers in 2 hours. What's the average speed? So this train is, to find the average speed, we add up all the distances, 190 plus 120, divided by the time, which is 3 hours plus 2 hours, or 310 kilometers divided by 5 hours. So your average speed was 62 kilometers per hour. So that's not bad. And again, that's an average speed, right? Trains go pretty fast. And the numbers will throw you off. It's not the same as miles per hour. And and if they give us miles per hour, more than likely we'll have to convert it to kilometers or meters. But they tell us specifically what is the average speed. So now instantaneous speed is to tell you how fast you're traveling at that instant in time. That's it. If we go back to this problem, at this instant in time, they were going 190 kilometers uh, in 3 hours. Now that might, if you looked at their speedometer, well, this is a better one. They traveled 120 kilometers in 2 hours, so they were probably going about 60 kilometers. So if you looked at their speedometer, um, it was probably close to 60. So what you see on a speedometer is basically instantaneous speed. It's average too, but the amount of time that they take to average it is very short and small. So the speedometer in a car measures the car's instantaneous speed. Note that the scale markings both give kilometers and miles per hour. So when we were talking about 88 kilometers per hour, that's about 55 miles per hour. And we said in that last problem, the train goes about 62 kilometers per hour. That's 35 miles per hour. So the orange stuff is the kilometers per hour, and the white numbers are the miles per hour. So how can you find speed from a distance time graph? Well, the slope of the line, when I graph the distance versus time, is actually the speed. So let's just jump in there. So I have this graph here of the distance traveled versus the time it takes to travel it. And so when I calculate the slope of this line, it's actually the speed of the car. So when I look at this, the first graph, it's traveling at a constant speed. So if I plot a graph and and we're gonna do some things on the carts when we do the lab where you can see this in real time. You guys are going to speed up the carts, slow down the carts, and you'll see how this changes. But the steeper the slope, the faster the speed. Okay, so graph A, it's going at a higher speed than graph B, and they're constant rates because it's a straight line. Now on graph C, what you'll notice is that right here, it's kind of going fast, and then from here, the car isn't really moving because the distance hasn't changed much. So from 8 to 12 seconds, it's not moving at all. Okay. So you can calculate those and see. And then up here, because this is 150 divided by 4 and this is 100 divided by 4, you have a faster speed up at the top here. So what's the difference between speed and velocity? You'll notice in the reading guide, a lot of times I offer you the answer speed or velocity. Well, velocity is a vector. And I'm going to say that a lot. I remember when I took physics for the first time, my teacher kept saying, this is a vector, that's a vector. And I thought, what the heck difference does it make? Well, a vector is, it's a measurement that has speed and a direction. And so, or you'll hear me say it has a magnitude and direction. So speed is the measurement or value of the distance versus time, right? When I say 88 kilometers per hour, the value is 88. That's my value. That's the number. But now if I say 88 kilometers heading due east, now it's a vector because I'm giving you a direction. Sometimes knowing the speed isn't enough. You also need to know the direction of the object. Together, the speed and the direction in which the object is moving is called velocity. Now, vectors are important because, and I'm not going to get too far off topic, but it really has to do with frame of reference. Okay, and we'll explore that after this lecture. I've got some worksheets I want to do with you guys. But a cheetah's speed may be as fast as 90 kilometers per hour. To describe the cheetah's velocity, you need to know the direction that it's moving. Vectors can also be used to show changes in motion. Vectors are varying lengths. Each vector corresponds to the velocity at a particular instant. Um, and it can represent motion. We have vectors for everything, for forces, and it's all related. Once you learn vector math, that's it. It's pretty easy, actually. The longer the vector is, the more value, the greater the number. So if I were to draw a vector on the board, and we'll see some slides of this, the vector for 62 miles per hour is shorter than the vector for 88. Vectors point in different directions to represent the direction at any moment. And so as a sailboat sails in a direction, it changes its velocity, and sometimes even if the speed stays the same. So how do we add these velocities? Well, this is what I was talking about, relative motion and combining velocity. So if we look at the first picture, we have the boat kind of floating with the current. So we have this little arrow here. Notice that this arrow is shorter than this arrow, but it represents the flow of the water at 5 kilometers per hour. So this is probably some little riverbank or something like that. And then the boat itself is traveling at 12 kilometers per hour. So then the question is, how fast is the boat really traveling? Well, if you were standing here on the shore, the boat would be traveling 17 kilometers per hour. Now, the second picture, or diagram or figure B, we have a boat that's traveling in this direction at 12 kilometers per hour, but the river is flowing this way at 5 kilometers per hour. So now that's going to change the speed of the boat and the direction of the boat. In other words, the boat is not going to end up here. So if we do the math on this, this one is going to travel at 17 kilometers per hour in this direction, and this one's going to travel at 13 kilometers per hour in this direction. And I'm going to stop with the assessment questions. We're going to do a lab on all this stuff, so I'm just going to wait. Okay. And that's it. Just go ahead and do your reading guides.